we've moved into the third period. Now we have to add an extra few sets of boxes. So we have now got the 3s boxes and the 3p boxes. This is the electron configuration for aluminium, which has got 13 electrons. It's in group 3a on the periodic table. So the inner shell is these 5 orbitals. So they're generally kind of shielded from any bonding or any external effects. They're very closely held to the nucleus. They're not really going to do any reaction or any chemistry of any note. So that means that we have these outer shell or valence or outer sort of the electrons which are going to be more susceptible to chemical reactions. So aluminium, 13 electrons. So in the inner shell, we have 2, 4, 6, 10 electrons, which means that we have 3 in the 3s orbitals, or the 3, n is equal to 3 orbitals. So here n is equal to 3. All right. So we can then fill in our sort of Aufbau diagram where we fill from lowest to highest energy. So like these electrons are going to be the ones which are inner shell. So there's going to be inner. They're not really reactive in any way. And then we have this outer group here where we have 2 electrons in the 3s and 1 in the 3p. Remember, we fill from lowest to highest energy, so increasing energy going from 3s to 3p. So our SPDF electron configuration is going to be 1s2, 2s2, 2p6, then 3s2, 3p1. There's 1 orbital in the 3 degenerate 3p orbitals. Okay. Another kind of notation that we find for Nobel or for electronic configurations is the Nobel gas notation. So in this case, we take what is generally termed as the core electrons or inner shell electrons and just sort of write them out using the elemental configuration of the nearest noble gas. So the electron configuration of an element can be represented as a function of the core electrons in terms of a noble gas and the valence electrons. So, well, I mean the preceding noble gas, not the next one. So the full electron configuration of SPDF notation for silicon is this. So 1s2, 2s2, 2p6, 3s2, 3p2. But we could remove this part, which is sort of the core or inner shell electrons, and those could be written out using the neon sort of neon in brackets. So square brackets neon gives the orbital box notation here for silicon. So we're really just looking at what is called the valence electrons or the outer shell electrons. So these are the ones which will be most active in bonding, most active chemically. And so then with the noble gas notation combined with this SPDF notation, we can have neon in square brackets 3s2, 3p2. That should be. So you can see then that this allows us to sort of speed things up a little bit, and we can remove some of this confusion with the inner shell. And so this is a very common notation that you will see. And so this is just the preceding noble gas. It could be helium, it could be neon, it could be argon, could be whatever. And so then we're just dealing with the outer shell electrons, the valence electrons, and so those are the ones that are generally of most interest. Noble gas configuration. So we'll give more examples on the board. So for example, let's go to lithium then, for example. So lithium, right, has atomic number 3. It has 3 electrons. So it is going to be 1s2, 2s1, right? So the preceding noble gas for that is helium. So it would be helium 2s1. Okay. We could do it then for carbon. So carbon has 6 electrons. It then has, so it's 1s2, 2s2, 2p2. And so it would also have helium as the preceding noble element, and so that would be a helium 2s 2p2 like that. We could also do others. So aluminium, which is right beside silicon. So aluminium is going to have 13 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p1. So its nearest noble gas would be neon. And so that would be neon 3s2, 3p1. Okay. And so you can do that for lots and lots of them going down the periodic table. It just adds more and more inner shell electrons, really. So here's it done for all of the elements in the periodic table. You can see that we've done, for example, lithium, we did carbon, we did aluminium. You could do it also for tin, where the nearest is krypton, and then it's krypton 4d10, 5d2, 5p2. And so this is just sort of like how you would do it for any element. Transition metals then, so all fourth period and beyond D block elements have an electronic configuration of AR, NS, X, N-1, DY. So what does that mean? Where N is the period and X, Y are particular to the element. So for example, if we have AR, we could have 4S, 2, 3D1, or whatever, something like this. So this number N is 4, and then it's N-1, so 4 minus 1 is 3, so that's where we get the 3 and the 4. So electronic configuration then for transition elements, so those are the ones in the D block, so are written by shell even though the electrons fill the period are filled by the periodic table. So for nickel, Ni, last electron to fill is the 3d8. So electronic configuration by filling is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. But the electron configuration by shell, so this is the way it's actually written, is 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2. So remember, we looked at this extensively at the start. How do we get the order of the filling? That's the n plus l. So here, n plus l is 4 plus 0, because s orbitals are 0, so that's 4. And then here it is 3 for the n plus 2 for the l is 5, and so that gets filled after this. So that's why the order of filling is like this. But the way that we write it out is in order of the shell, so by a principal quantum number. So we go from n is lowest to n is low to n is high. Okay. So you can see it here for a bunch of different elements. So like as we go across the fourth period, so calcium through zinc. So this is the fourth row of the periodic table. So calcium has argon and then 4s2. So we'll be using argon the whole way through, and then the valence electrons only. We're looking at 3d and 4s. So you can see that calcium has no 3d electrons, but it does have full 4s. Scandium then, it has 1d electron, so it's 3d1, 4s2. Titanium then has 2d electrons, and you can see we're filling here via this n plus l rule, so always 4s first in the elemental form. So whenever we're dealing with just elements, n plus l, we fill up the 4s first and then the 3d. We're also following the Hund's rule, where we're filling empty orbitals before we are pairing any electrons. So initially we're going through where 1d electron for scandium, 2 for titanium, 3d electrons for vanadium, Chromium has a split system, so it's a little bit different. So it takes an electron. So we don't go from 3 to 4. We actually go from 3 to 5 d electrons. And why is that? Because we take one away from the 4s orbitals. Now, why this is will not be immediately apparent. It's just whenever we have a chance to either half fill all the orbitals or fully fill them, as we'll see with copper, we take away an electron. So there's no D4 here. There's only the D5. And then we go to the next one. It's manganese is 3D5, 4s2. So the s electron or the s electron is replaced. Iron is 3D6, 4s2. And then we keep going down. And we get the same thing happening at copper as we did with chromium, in that we take an s electron in order to completely fill this these d electrons for the copper. And so the reason for this is because it's going to have a better energetic effect. So it's going to end up giving the element a lower overall energy. And so for chromium and copper, the same things happen. If you're really interested, you can have a look here at transition metal electronic configurations, page 263. That's quite a bit further on in the book than we are right now. But if you're really interested to know that, that's why. But it's a little bit beyond what we're looking at right now. So concept check. So which orbitals are not allowed? So just have a quick check and see what you think, 5 or 10 seconds. Pause if you need more time. I don't think you will, but always available. Answer coming soon. Okay, so the answer here is the 2D, because remember that whenever these numbers are the principal quantum numbers, so n, so if n is equal to 2, we can have L values of 0 and 1. L can be equal to 0 and 1. So 0 is S and 1 is P. We don't have d orbitals being allowed in this, in n is equal to 2. Which orbital above is highest in energy? Again, 5 or 10 seconds. Answer coming soon. Pause if you need more time. Pause if you need more time. Okay, so you might think that it's this one because it's got a higher principal quantum number, n is equal to 5, but it's actually going to be the 4f, which is higher in energy. So the 5s will be filled before the 4f will be filled. So which orbital above is lowest in energy? And 5 or 10 seconds. All right, so this is easier. So this is just 3p. This orbital doesn't exist, so that cannot be lowest in energy. How many unpaired electrons are in the ground state electronic configuration of selenium? Five or 10 seconds. Okay, so selenium has the electronic configuration of AR what's this, 3D10, 4S2, 4P6, 4P4. Oh. So if we draw those out as boxes, I won't draw out the D electrons because that's going to take up too much time. Then we have that's the S, that's the S. And then we have the P. So we have 1, 2, 3, 4 p electrons. So that means we're going to have 2 unpaired electrons. What is the maximum number of electrons that can occupy a set of f orbitals? So think about how many f orbitals there are based on the L value of the f orbital. 5 or 10 seconds. Pause if you need more time. Answer coming soon. Okay, so remember that when L is equal to 0, we have s orbitals. 1, we have p orbitals. 2, we have d orbitals. And 3, we have f orbitals. So the number of ml values for each L value is equal to 2L plus 1. So 2L plus 1. So it's going to be 2 times 3 is equal to 6 plus 1 is equal to 7. Then 2 electrons per orbital. So 7 times 2 means we have 14. Alrighty. What is the complete electronic configuration for phosphorus? So this is the complete SPDF, or you can even draw boxes if you really wanted. 5 or 10 seconds. Think about it carefully. Pause if you need more time. Okay, so phosphorus is in the second row, so it comes somewhat after aluminium. It is in group 5 below nitrogen, so it's got 5 valence electrons. So it is 1s2, 2s2, I was about to write a p, 2p6, 3s2, 3p3. Bonus question, how many valence or how many unpaired electrons does phosphorus have? Think about that. What is the orbital box notation for fluorine? So fluorine is in the second row of the periodic table, so it's 1s, 2, 2s2, 2p5. So we draw out the boxes. So there's one box, so it's the s electrons, the 1s electrons, then 2s electrons. Okay, so that's 2s, 1s. Then we have the p orbital, so there's 1, 2, 3 p orbitals, so those are 2 p orbitals. So we have 1, 2, 3, 4, 5 p electrons. So that's the orbital box notation for fluorine. What is the noble gas electron configuration for arsenic? So arsenic is on the 4th row of the periodic table. So it means it's going to have argon as its preceding noble element. So argon, then it's going to have 3d10, 4s2, and it is in group 5a, so that's going to be 4p3. That should be a 3. That's even worse. Okay. All right. Moving on then, we've done atoms, neutral atoms. So now let's consider what happens whenever we have either a deficiency of electrons. So that means we have a positively charged ion, a cation, or if we have an excess of electrons, we have a negatively charged system with a abundance of electrons. That is an anion. So write the electron configuration of the neutral atom. Remove electrons. So in order to get the electron configuration of ions, we first write out the electron configuration of the neutral atom. Then we remove the electrons from the orbital with the highest principal quantum number, i.e. the highest value of n. So it could be like, the highest value of n. So for example, here in iron, we have the noble gas notation here. So we have argon 4s2, 3d6. So we're going to be wanting to remove it from the 4s. So what are my options? A, B, C, or D? What do we think? Based on these rules. 5 or 10 seconds to think about your answer. Pause if you need more time. If not, we can go on to the answer very soon. All right, so the answer is going to be this one here. So we're removing from the highest principal quantum number. So this is actually the neutral configuration. So this is not iron 2+. This one is the answer because we've removed it from the higher principal quantum number, which is 4. So we've also, this one is also removing it from the 3, n is equal to 3 level. this one is removing, well, this is just wrong. It's got too few electrons for a F2 plus. So electron configuration of ions. How do we know the configuration of ions? So we know this by the magnetic properties of the ions. So here we have iron 3 oxide inside of this syringe. We can see then that if we use a magnet, it can be swung towards the magnet. It is attracted towards the magnet. So this iron 3 oxide is going to be magnetic, ferromagnetic, or, well, at least paramagnetic. So do we remember? I mean, we covered this some time ago. Iron 3 oxide. So what is the formula for iron 3 oxide, and what is the charge on the iron ion here? How do we think about that? Make sure you know how to do that. If you don't, please review the earlier lectures. So ions with unpaired electrons are paramagnetic, so they're attracted to a magnetic field. Ions with paired electrons are diamagnetic. They're not attracted to a magnetic field. So this is a typo in their slides. Ions with, oh, without, never mind. It is right. My bad. I can't read. All right, so so ions without unpaired electrons are diamagnetic, not attracted to a magnetic field. So iron 3 plus ions in Fe2O3, so this is now the answer to that previous question. So iron 3 oxide, so it's iron 3 plus, like this, and then they're going to be Fe2O3, because remember oxide is O2 minus. Have 5 unpaired electrons. This makes the sample paramagnetic. So remember earlier, we said that Fe2 plus has the electronic configuration of argon, what's that, 3d6. So we remove one more electron, we get argon 3d5 for iron 3 plus. Then if we do the orbital notation, so we have 5d orbitals. We fill them all like before we can pair them, we have to fill empty orbitals. And so we have here 5 unpaired electrons, which makes the sample paramagnetic. It's very paramagnetic, in fact. So this is sort of group work. I guess there's no group work here. So what I'm going to ask you to do is take a moment to pause the video, do the electronic configurations of potassium plus and arsenic 3 plus, and then we'll do it together. So pause if you need more time. I'll give you about 5 or 10 seconds. Should be enough. Pause if you need more time. Okay, so you can do it. You can do it the whole way out. You can do orbital notation, whatever works for you. I'm not asking for a particular version right now, but I'm going to do it in noble gas notation because that'll be faster. So potassium then has, as a base, is argon, and then it's going to be what, that 4s1. So we're losing here these, so it basically has the same electronic configuration as argon. Arsenic 3 plus, I think, is also in the same period. Yeah, so it's got the same AR. So we'll do out the elemental notation first, and then we'll remove electrons to form the cation. So it's argon, then it's going to be 3d10. It's going to be 4s2, and then I think it's below nitrogen, right? Yeah, so it's going to be 4p3. Okay, it's got 5 valence electrons in the n is equal to 4 shell. So we're going to remove 3 electrons. So the 3 that we're going to remove are these electrons here. So they were the last in, so they're the first out. Whenever we're counting and filling in our valence shells. Okay, so these are the electronic configurations for both of those. Concept check then. So which element has the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10? Is it nickel, iron, zinc, or argon? Think about it. Pause if you need more time. Okay, so we see here that we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So the one here, which is going to fill this, so we're looking for something which has 2, 4, 10, 12, 18, 28 electrons, and so that would be nickel. So our answer here is nickel. Is the electron configuration above a ground state or an excited state? Ground state, excited state cannot be determined. Again, 5 or 10 seconds to think about this. Pause if you need more time. So most likely this is going to be an excited state. The reason for that is that nickel would typically not have 3d10 in its elemental nickel form. Usually it would have something like 1s2, 2s2, 2p6, 3s2, 3d8, 4s2. But in this sort of excited state, we could promote 2 electrons into the d level, and it could be an excited state. So the most stable configuration will be that with the total lowest energy. So there is some stability of half-filled sets of orbitals. We saw that with chromium, and we saw that with iron, or not iron, chromium and copper. For the following, write out the electron configuration for both, then use the orbital filling diagram. So what we might think that we should do is, well, we saw this earlier, but we'll do out the noble gas sort of notation. So chromium is argon, what's this, 3d4, 4s2, if we're like being super strict about filling in the lowest energy to the highest energy. But what actually ends up happening is this anomaly where the stability of half-filled sets of orbitals or fully filled orbitals, like shells, subshells, is actually more beneficial for the energetics of the system rather than having 4s2 being filled. So for example, if we draw out the orbital splitting diagram, so here we have the 4s, or well, no, we'll do the d's first. Okay, and then s, and then we'll do for copper, we'll do it over here. So there's 1, 2, 3, 4, 5d orbitals. Those are the 3d. This is the 3d over here, the 4s, and then the 4s here. Okay, so if we fill it in based on the configurations we've given here, for chromium we would have 1, 2, 3, 4, and then 2 in the 4s, like so. And then for this one, for copper, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, hang on. Got carried away there. Erase that one. Okay. And then 4s would be filled. Okay, so that would be what we would assume if we didn't have some chemical knowledge of this anomaly where the stability of the half-filled sets of orbitals or fully filled shells subshells is going to be greater. So the subshell, the d subshell here, the energy gain from being half fit for all the orbitals to be half filled means that we're going to have a transfer of an electron from here to here. And the same thing is going to happen with the copper. It's going to transfer an electron from the 4s into the 3d so that all of the 3d orbitals can be filled. And that's a very positive energy change for the copper and the chromium. Both of them become lower in energy as a result of this, and so they become more stable. So it becomes the most stable configuration. Periodic properties then. So periodic properties are what happens as we go across the periodic table. So elements were first arranged by increasing atomic number, and periodic tables were arranged before electron configurations of elements were known. Properties of elements are periodic, so we saw this from the Mendeleev-Mayer periodic tables. So remember that Mayer had the worst publicist, Mendeleev had a better publicist, and so we remember Mendeleev as the creator of the periodic table, but Lothar Meyer also had a pretty good one, just not as popular. So we saw this before where the Dmitry Mendeleev was able to predict very accurately some like the properties of germanium, which hadn't actually been discovered whenever he created his periodic table, but based on the elements surrounding it, he was able to get these accurate predictions. So 15 years before it was found, he was able to determine its atomic weight very accurately, its density very accurately, its specific heat well. Melting point, of course, is high, color is gray, but it's not so bad. The formula of the oxide perfectly, the density almost perfectly, the formula of the chloride perfectly, the density of the chloride pretty good, and the boiling point of the chloride also pretty good. So this was all without actually having germanium to work with. And it was based entirely on this periodic table. And so one of the reasons why the periodic table of Mendeleev became so widespread was because it turned out that he was right about a lot of things with regards to the elements. So general periodic trends, so atomic and ionic size change, ionization energies change, and electron affinities change. So atomic sizes. So atomic radii generally increase as we go from left to right. We have larger orbitals, they're more diffuse, they're not held as tightly. Our effective nuclear charge is changing, it's getting less. So the outer shell electrons our effective nuclear charge is increasing, but our outer shell electrons are further away, and so they're held less tightly. So the atomic size for main group elements, atomic radii generally increase going across and also going down, because we're adding more electrons to the same n level. So they're having a higher effective nuclear charge and they're held more tightly. But as we go down, there are larger orbitals and electrons are held less tightly. Okay. So effective nuclear charge, the Z star, this was something we learned about earlier. So the 2s electron penetrates the region occupied by the 1s electron. The 2s electron experiences a higher positive charge than expected. So effective nuclear charge, the Z star experienced by electrons in the valence orbitals, so increases in Z star across the period. So here we're going from lithium, beryllium, boron. So we're going across the periodic table here, not down it. So these are calculated values based on Slater's rules. So we can see that the Z star experienced by electrons in the valence orbitals is this. So this is the pull. So the pull of them is increasing as we go across. So the valence electrons are held more tightly in fluorine than they are in lithium. And why is this? Well, we're adding we're adding electrons as we go across the periodic table. We're adding electrons to the same shell, so the same n value. This means that they're not those electrons are at the same distance, more or less, from the nucleus in at least these 6 or these 5. These are all these electrons are held at approximately the same, or the same principal quantum number n. So they're not getting further and further away from the nucleus, but the nucleus is getting more and more positive. So the nucleus gets more and more positive as more protons are added there, but the electrons are not moving further away. And so that means that the electrons are feeling more positive pull. And so that's why the effective nuclear charge of the electrons is higher in fluorine than it is in boron. So orbital energies drop as Z star increases. So here we have for sodium, magnesium, aluminium, as we go across, we can see that the orbital energies are decreasing as we go across the periodic table. So the 1s orbitals are lower in energy for argon than they are in sodium. And they're like the 4s orbitals are higher in energy for sodium than they are in argon. So it's going down like that. So if we think about this, we can consider chlorine, so Cl2. So this is a molecule of the element. So the distance between the two nuclei is called the bond distance. So in chlorine, it's 198 picometers. If the two atoms which make up the molecule are the same, then half the bond distance is called the covalent radius of the atom. So the covalent radius of chlorine is 198 picometers divided by 2 is 99 picometers. So the distance between this nucleus and this nucleus is 198. So half of that is 99, which is the covalent radius. If one knows the bond distance in a heteronuclear bond, then the radius of another atom can be estimated. So the radius of the carbon atom can be estimated based on the covalent radius of the chlorine. So we would say that the radius of the carbon is 77 picometers because the bond distance, i.e. the internuclear distance between carbon and chlorine, is 176 picometers. So it's 176 minus 99, which is the covalent radius of chlorine, which gives us 77 picometers as the sort of radius from the nucleus to the edge. This is R value, R carbon. Okay. So there are periodic trends in size. So it assumes that the atoms touch each other and the atomic radius is a half of the diameter. So these are some assumptions that we're making. So effective nuclear charge and the same principal quantum number n. So this is kind of what I was talking about earlier with regards to fluorine versus boron. They're all the same principal quantum number, but more and more electrons are being added to that same shell. And so they're not getting further away, because to get further away, they need to be put into different shells or higher quantum principal quantum numbers. So the screening of valence electrons is by the core electrons. So ZF is equal to Z minus S. So S is the screening electrons. So Z is the atomic number, the number of protons. S is the number of core electrons, those doing the screening. So for example, for sodium, we have 11 E minus 10 core electrons is equal to 1 plus for the effective nuclear charge. Magnesium is then 2 plus. So why is this? So as we go from right to left on the periodic table, nuclear charge decreases and size increases. And then as we go down, size increases, size and charge increase. So down a group, the larger size, the more important than, so down a group, larger size is more important than the larger nuclear charge. But across a period, n is the same, but the effective nuclear charge increases. So what we see is that on the right-hand side, it should be that those are smaller because the outer electrons are held tighter because they experience a higher effective nuclear charge. Because if we think about it here, so fluorine has, so F has 17 electrons. And then it only has, it still has, it has the, is that right? 17 electrons? No, that's chlorine has 17 electrons. Fluorine has, so, okay, let's do chlorine. It's a better example. Chlorine has, is in the same period as sodium and magnesium. So it has 17 electrons and it has 10 core electrons. Which means that it has an effective nuclear charge for these valence electrons of 7 plus. So those are held much tighter than the sodium and magnesium. And so you would expect to see that the size of the chlorine would be less than the sodium or magnesium. And so atomic radii then, just in summary, so if we have two elements that are the same, like carbon here, chlorine here, and chlorine here, we would have what's called covalent radius, which is half of the internuclear distance, because they're the same. So the assumption is that they are equally spaced, like half of this distance comes from carbon and half from this carbon, half from this chlorine and half from this chlorine. Whereas in the case of a hetero system or a heterogeneous bond, so we have a carbon and a chlorine, we would expect that the distance would be half the covalent radius of the carbon and half the covalent radius of the chlorine. So this would be what 99 is what it is for chlorine, and so this is 72. No, 77. So we would assume that 77 plus 99 is going to give us the CCl bond. So it is 176. So 99 plus 77 is 176. Here we have a crystalline solid. So for example, aluminium. So a distance, so pictured here is a tiny piece of an aluminium crystal. Each sphere represents an aluminium atom. Measuring the distance shown allows a scientist to estimate the radius of an aluminium atom. So the distance from here to here is equivalent to 4 times the aluminium atom radius. So we're going through this from this nucleus through this nucleus to this nucleus. So that's 3 nuclei. So 1r, 2r, because 2r is equal to d being the diameter, and then 1r again. So that's 4r is equal to that distance. So here's the line: 1r, 2r's, 3r's, 4r's. And then I think that will do us for this session, and we'll pick it up next time where we'll continue talking about these atomic trends. So thank you for watching. See you.